We've defined the inverse trigonometric functions, arc cosine, arcsine, and arctan, as the partial inverses, let's say, to cosine, sine, and tan. So when I say partial, what I mean is we aren't truly having an inverses because cosine, sine, and tangent aren't one-to-one, so they don't have inverses. However, if we restrict cosine, sine, and tan to an appropriate domain, then they become one-to-one, and we can find inverses. And that's what arc cos, arc sine, and arc tan are. So this is a really important point. Important. So arc cos, arc sine, and arc tan are not, like I said, true inverses. True inverses to cos, sine, and tan. They're only inverses to these functions restricted. Now, what are important properties of inverses? Important properties of inverses are the cancellation properties, which basically means if I compose a function with its inverse, it doesn't do anything, right? It's a very boring function. So if I have f composed with f of x, and I feed in x, just x comes out, right? Nothing exciting happens, right? Because it's undoing the function. It's the job of the inverse. So that's an example of something called a cancellation property. So because arc sine, arc cosine, and arc tan are not true inverses, the cancellation properties are a bit delicate. So this implies that the cancellation properties we've seen for inverses only work for restricted domains. So let me just point out what I mean. Only work for restricted domains. So as an example, if I was talking about cosine, so for cosine, well, arc cosine composed with cosine of x. Right, it's extremely tempting to think this is just equal to x for any value of x. But that's not going to be true, is it, right? Because when we're talking about the inverse, this cosine is only allowed to have inputs which are in the appropriate restriction. So this is only true for x in the restriction, and the convention we had was the restriction for cosine is 0 to pi. So this is a really subtle point, right? It means if you want to kind of undo a cosine and you're going to use arc cosine, you're going to have to think really carefully about the value of x. If x is not in the appropriate interval, it's not going to work. So this means when dealing with trigonometric equations, if we're going to try to kind of undo them using inverse trigs, we've got to be ridiculously careful. So I think we should do an example where this kind of comes into full force. This is an example which is extremely similar to questions I've set on midterms before in first calculus classes. So quite a simple looking problem. I want us to write arc cosine, so let's keep the same situation, of cos of x. What am I saying? I'm being foolish. So cos of 7 pi over 6, let's say, in the form, so I kind of want to simplify this. So specifically I want to write it in the form a pi divided by b, let's say, right? Where a and b are integers, whole numbers. Can I do this? So I look at this and I say to myself, oh well, arc cosine is the inverse of cosine, so surely that means it's just going to undo it, it's just going to be 7 pi over 6. So that is dead wrong. Wrong. So arc cos is inverse to cos implies, well, surely therefore by the cancellation property, arc cos of cos 7 pi over 6 is equal to 7 pi over 6. Now let me just point out why this can't possibly be correct. Just for a moment, imagine this was equal to x. Just change the notation a bit. This would be saying that arc cos of some number x is equal to 7 pi over 6. What's the range of arc cos? Let's think about the graph. This is the graph of arc cos. The range of arc cos is 0 to pi. And 7 pi over 6 is not in the range. So this can't be correct. This can't be right. Can't be correct, as 7 pi over 6 is outside the range of arc cos, which is the closed interval 0 to pi. Whoa. So before I even start, that can't be right. But I do know something. Just as I've written up here at the top, I know that the cancellation property holds as long as the input into cos is in the appropriate range or the appropriate interval. So this is the correct thing to do. And again, it's not easy. I'm going to this example because it's quite subtle, right? So this is true, right, if x is in the appropriate restriction. So if that were true, awesome. Everything would be good. So what do we need? What we really need is to come up with an x such that this thing here and this thing here are equal to each other. And I need an x in the interval 0 to pi. So we need an x in the appropriate restricted domain such that cos of x is equal to cos of 7 pi over 6. Because if I have that, then all I've got to do is take, well, this guy, 7 pi over 6, cos 7 pi over 6, replace it with my cos x, but then I've got the cancellation property. So I'm basically done. So what do we need? We need to work out a value of x in the appropriate range between 0 and pi with the property that has the same value of cosine. So if you remember, this is exactly the type of problem we thought about when we were doing equal values for functions cosine, sine, and cos. So let's draw a unit circle. So these problems are just so difficult without truly understanding the definition in terms of the unit circle. So as always, this is your x, this is your y. Actually, maybe I shouldn't. It's fine, I'll just label it as usual. Okay, so what are we doing? So our angle is 7 pi over 6. 7 pi over 6 is all the way around here, isn't it? Okay, so this is my angle. Seven pi over 6. And that ain't no good because of the fact I'm outside of the appropriate domain. I need to be between 0 and pi. But remember what cosine is. Cosine is the x coordinate. So let's mark the points on this which have the same x coordinate, namely these two positions here. So the x coordinate there is the same as the x coordinate there. All right, so that's going to draw out here. What do I need? Now, why have I done this? We need to have an angle which is between 0 and pi. So in particular, the angles which are between 0 and pi are the ones that occur on top. Right? These are the angles between 0 and pi. And thankfully, by reflecting up, I'm getting an angle which works. So what is that angle? I've got to work this out, don't I? So this angle is, it's going to be kind of, first of all, it's pi, and then it's pi over 6 around. So that means that angle there is pi over 6. That means this angle, so you've got to really think carefully here, this angle around, which is what I want because it's in the appropriate interval, is 5 pi over 6. So what does all this tell me? These guys are the same coordinate. This is telling me that cos of 5 pi over 6 is equal to cos of 7 pi over 6. So let's get this carefully written out. So finally, arc cosine of cos 7 pi over 6 is equal to, well, these two are exactly the same now, right? I've really carefully thought this through. So this is arc cosine of cosine of 5 pi over 6. But now, and this is the crucial thing, this is in the appropriate restriction. And because it's in there, I know the cancellation property holds, because arc cosine is the inverse to cos restricted to that interval. So this comes out to be what? It comes out to be 5 pi over 6. Super duper clever. So this is a really good example, I think. It illustrates subtle issues to do with the definitions of the arc cosine. It would be the same kind of story for arc sine if you're doing it with arc sine. If you were outside of the range, you would need something with the same y value. So, for example, a point with the same y value as this would be over here. And that would be in the appropriate position, because for arc sine, you've got to be on this side. Same thing with arc tan. So you could go through almost exactly the same procedure. So really good example. Pretty difficult, but a classic kind of midterm or indeed final exam type question to really understand the details of this. All right, let's do another example. So this one is going to be kind of a classic trigonometric equation, right? So we need to find, so let's say find all theta such that, okay, so let's do something similar again, but let's do cos of theta is equal to minus 2 over 3. Now, before we do anything, minus 2 over 3 is not one of my special values, so neither is 2 over 3, right? So theta is not going to be one of my neat answers, which is kind of pi over 6, pi over 3, or pi over 4, or something like that. So I know I'm probably going to have to use an inverse trigonometric function. So looking at this, again, you want to do the same thing, don't you? You want to take arc cosine of both sides and then kind of cancel things off. But that can't be right because, well, not in total right, because there have to be infinitely many solutions to this. Because cosine, remember, takes the value minus pi over 2 infinitely many times. So again, as with all things, I think we should draw a picture to wrap our heads around exactly what's going on. So same story. Let's draw the unit circle and try to kind of wrap our heads around everything that's happening here. So y here, x here. not going to work. Be a little bit smaller. Good enough for me. All right. So cos theta is minus 2/3. So cos, remember, is the x coordinate. So let's do the following. Let's draw a vertical line at the position minus 2/3. So this is giving all the positions where the x coordinate is minus 2/3. Let me label in some other points as always. This is 1, -1, 1, -1. So what are the possible positions on the x-axis where the x coordinate is minus 2/3? It's these two positions here. It's that, and it's also that. So these two positions, there and there. So I've got to come up with a way to describe all angles which give those two positions. That's the deal here. Now, let's label some stuff. So the angle around the top, let's label this as alpha, let's say, right? So I don't know what that is at the moment. Now, around the bottom, let's label this as minus alpha. Pretty simple, right? So that obviously is negative, it's around the bottom. So really what I need to do is work out alpha before I do anything. So I need to work out alpha. So let's think about this. If I'm going to do arc cosine of minus 2/3, what's it going to give me? So remember what the output is of arc cosine. So the output of arc cosine has to be all numbers which are, well, the range is it's 0 to pi. So it's this same story. Okay? So again, arc cosine is defined after restricting cosine to the domain 0 to pi. That means the range of arc cosine is 0 to pi. So what does that mean? Well, that means from the way I've drawn it, because of the fact alpha is in the range of arc cosines, this is not easy. Because it's in the range of arc cosine, this means alpha is equal to arc cosine of minus 2/3. Now, why is it not equal to minus alpha? Well, that's because it's not in the range, right? It can't possibly be minus alpha from the way I've set things up, because it would have to be down here. But that's not where the range of arc cosine is. So very subtle, right? So this here on top, this is the range of arc cosine. So what does this tell me? Well, that means this point. So I should do this in red, I suppose. So this tells me this here is going to correspond to what? Well, this corresponds to, well, this is minus alpha. So minus alpha is minus arc cosine of minus 2/3, isn't it? So I basically just need to describe these 2 points. And that's not too bad, because to describe these 2 points, as always, once I've got one angle describing them, I can describe all other possibles by doing full rotations around. So I know what alpha is. It's arc cosine of minus 2/3. All these other ones are going to be 2 pi times k, an integer, plus it, right? Same deal with the bottom, but with minus. So the following is true. So cosine of theta is equal to minus 2/3 if and only if theta has to be equal. There are 2 possibilities. Theta plus 2 pi k, full revolutions, or theta is equal to minus, in fact I don't need the theta there, do I? It's equal to just minus alpha plus 2 pi k. Those are the two possibilities. It's giving those two locations. But now I know what alpha is. So this is if and only if this is equal to arc cosine minus 2 over 3. Arc cosine minus 2 over 3. Remember, arc cosine is neither odd nor even, so I can't simplify this or anything like this. Plus 2 pi k. So again, let's just make sure we understand k is an integer here as always. Or minus arc cosine minus 2 over 3 plus 2 pi k. So that's a very difficult example. Those are all possible solutions to this, all of them. And the last thing I want to do is to relate this back to the graph of cosine, because I think it's a good idea to know some of the things to look out for in the graph and why they're turning up. So in terms of the graph, what do we have? So you can try doing this with a graph alone, but it's pretty difficult, right? Because you've got to be so careful about what arc cosine means. But let's take the graph of cosine. So let's do it in green. Is that how I've been doing cosine the whole time? So I'll try and do this reasonably accurately. So let's mark my two kind of upper and lower bounds, minus 1 and 1. And let's attempt to draw this nicely. So not too bad. Okay. So it's going to be that repeating, isn't it? Almost. So maybe I should do the following. I've got a plan. Here we go. So this is what cosine looks like. This is y as cos of theta. So of course I've got theta here and I've got y as my coordinate here. Alright, so what's going down? So we're taking, so of course these two positions, this is 1 and this is minus 1 down here. So let's get rid of these, and the line of interest to us is the line at y is equal to minus 2/3. So it's going to be somewhere around about there probably. So this is y is equal to minus 2/3. So what are we interested in? We're interested in all these positions. These are all the locations where I'm getting a solution. And what are we picking up? Well, first of all, let me just mark a few points. So remember, this point here is pi. This point here is minus pi. So this location here, that's your alpha. So this is your alpha. I think we need to be a bit smaller. This is your alpha, which equals arc cos of pi minus 2 over 3. And this location here, this is kind of your minus alpha, which of course is equal to minus arc cos of minus 2 pi over 3. Not easy. But then remember, we've got this repetition. And the repetition is going to be where I'm adding full revolutions to each of these. So for example, adding 2 pi to minus alpha. So adding 2 pi to that brings me over to what? It brings me over to this location here, right there. So we have this kind of symmetry, if you want. The solutions are kind of sitting at the bottom of these troughs, the bottom of these valleys, and they're the same. They're kind of symmetric around the kind of the central point. So maybe something to say would be the following: if I was to draw a vertical line through this, then this length here to there and there, and this length here are the same. And this can all be backed up with a unit circle, but it's kind of just nice. It's terribly drawn. So that length and the other length are equal. So these are the same length. So this is just pointing out various properties that are nice to be aware of when it comes to the graph. We don't really need this, but it's just nice to know some of the stuff to look out for. So yeah, trying to do this purely with a graph isn't a disaster, but it is a good idea to have the unit circle in your mind because of the nature of what you're doing, right? Because you're trying to solve cos of theta is equal to minus 2 over 3. So if you're trying to use the arc cosine function, which you really want to because of the fact minus 2 over 3 isn't a special value, you can't use it easily unless you work out what theta between 0 and pi gives you this. Okay, and you've got to kind of draw a picture to be kind of really on top of exactly what's going on. So this is a very difficult example, but it really is about as difficult as it gets as far as I'm concerned. It kind of hits all the kind of the key difficulties with inverse trigonometric functions. So I'd really counsel you to take a lot of time really understanding every detail of this. All of these little statements I'm making, all of the kind of little comments about ranges have to be this, domains have to be that, this may work, it may not work. Take the time to understand them, because that's going to be really the key to truly excelling in calculus in the future, is that kind of detailed understanding of each concept, understanding the kind of the minute things that can go wrong, that might work, things like that, right? The really detailed aspect of things.